Ready? Hello? Hello? Testing. Okay. Well, welcome to everyone who's not at NAPS. So hope you're enjoying. Hope you're enjoying your Monday. Our first speaker of the session is T. Xu. T received his BS in electrical engineering from In
清华
Tsinghua University. He is currently a master's candidate working with Professor Gross. Thank you.
Hello everyone. You can try this here. Hello everyone. In today's presentation, I'm going to describe construction of a probabilistic simulation tool for systems with integrated concentrated solar plants. The concentrated solar plant technology is a promising approach to harness the solar energy with several important implementation around the world. The CSP technology utilizes the mirrors with tracking systems to collect the direct normal irradiation of the sunshine, and the CSP will collect solar energy into thermal energy. The thermal energy will be used to produce the electricity in the steam turbine or heat engine. Some of the CSP are equipped with the thermal energy storage, which can store some thermal energy for later use. So unlike the PV system, a CSP plant with thermal energy storage can generate the electricity outside the sunrise and to sunset periods. Here I'm going to describe briefly how the CSP works. After the sunrise, the mirrors collect the solar energy to heat up the transfer fluid. The thermal energy contained in the transfer fluid will be used to generate the steam, which are delivered to the steam engine and the generator for electricity production. Some of the CSP are equipped with the storage. So during the day, the fraction of the thermal energy will be stored in the storage. After the sun sets, the solar energy is not available anymore, so the plant will use the thermal energy in the storage to continue to provide the electricity. In my paper, I aim to construct a practical simulation tool to emulate the behavior of the power systems with integrated simulation, integrated CSP resources. I will present some of the representative results to give us insight of the impact of the CSP resources and demonstrate this approach's capabilities. At first, I will describe the construction of the CSP power output model and its incorporation into the production simulation tool. I will give up some illustrative study results and also the concluding remarks at the end. At first, we can see a plot of the solar energy we can get in Las Vegas. On July 2nd, the solar energy is very stable. I think it must be a very a clear day. But 5 days later, the direct normal irradiation changes frequently. I think there must have some cloud cover or some very terrible weather happened that day. But more importantly, we care about how much we can generate every day and how much we should supply the demand. For example, on Monday afternoon, the CSP almost works at a full capacity while the load is very high. But on Thursday afternoon, the CSP's output is almost zero when the load is at its peak. So the weakly correlated behavior has a huge impact on the impacts of the CSP resource on the power system. The uncertain and the variable and intermittent DNI has a huge impact on the times and amount of the CSP energy production. And the CSP also has limited controllability and dispatchability because we cannot ask the sun to shine in the evening or like do not shine in the afternoon. So, but the deployment of the thermal energy storage provides some considerable flexibility in the CSP operation and the energy production. The conventional in order to quantify the impacts of the CSP resources, we need to modify and extend the conventional probabilistic production simulation to incorporate the time-varying CSP resources. Such an extension needs to consider the uncertainty of the loads and the resource, the correlations among the resources and the loads, and the flexibility of the thermal energy storage, because we can use the storage to shape the CSP output as we want. In my study, I consider as different the CSP sites. All the collected data are simultaneously measured at each site, because in this way we can represent and we can capture and represent the geographic and the temporal correlation among the CSP sites. Because, for example, there is a cloud cover over the Champagne at 12 p.m. At 12 p.m., maybe 1 hour later, the cloud cover will move to Chicago. So if there are two sites located in Champaign and in Chicago, there may be some relations and correlation between the two sites' output. But the solar energy is only available during the sunrise to sunset, which varies throughout a year with its peak during the summer. So in order to have a meaningful analysis of the solar energy we have every day, we introduce a scaling scheme to map the actual daily shapes into a common time scale for all the sunrise to sunset periods. With in my study, I denote the J as a number of the equal time scale subperiods in all the sunrise to sunset period. Here, the two plot here gives us an example of the scaling process in summer with the J equal to 15. We can see we scale all the actual daily DNI shape into the time scale the DNI shape here. So after scaling all the collect DNI data, we can extract the daily multi-site DNI information and represent their correlations by joining the time scaled DNI shapes together for one particular day to get the time scaled DNI samples for all the sites. The D samples forms the time scaled DNI shape collections. The collections is based on one single time frame. So it allows us to identify the similar DNI shape in a meaningful way. In my work, I use a k-means clustering algorithm to divide the actual DNI shapes collection into R different clusters. Each cluster is a subset of the collection with the similar daily DNI shape. And for each cluster, we refer the cluster and its probability as the regime. So we use the R regimes to probabilistically characterize the solar resources in our simulation. In each regime, we can draw samples to simulate the daily CSP outputs. But we should remember we do scaling first. We have to invert scale to the actual sunrise, sunset of day D for the simulation. Otherwise, it's like meaningless. Without storage, the CSP power output is directly determined by how much solar energy we can get from the sun. With the storage, we can store some thermal energy for later use in the day, and we can shape the output as we like. For example, we want to maximize the CSP output. We want to maximize the volume of the energy of the CSP power output. Also, we can also set up some objective to make the output as smooth as possible. So it depends on what do we need. Here I'm giving the information flow in the CSP power output model. Without CSP, we map the DNI data into daily power output data using the instantaneous CSP output model. If we consider the thermal energy storage, we set up some scheduler to shape the CSP power output model. In the storage scheduler, we set up some objective to optimize the contribution from the CSP. In this work, the objective is to maximize the volume of the CSP energy. But we should know the optimization problem has some constraint on the energy balance in the storage, the discharging limits, the physical capability, and the thermal energy inputs for the energy production. For example, we cannot put like 1,000 megawatt hour into the power block at 1 hour because it's so huge, the power block cannot stand with so many energy we input. But we should see that the time frame used in the model should be the same as the time frame used in the simulation study. We decompose the multi-year study period into T long overlapping simulation periods. In each simulation period, we assume that there are no changes in the resource mix, unit commitment, and policy environment worker. Such change may happen in the subsequent periods. We choose like a week as the simulation period, and we pick up some representative weeks to simulate in our work. We also choose hourly subperiod as the smallest indecomposable unit of time. In each subperiod, we assume the system is in the steady state and all the shorter duration phenomena are ignored in one subperiod. After we constructing the CSP output, we utilize the conditional probability concept to incorporate the probabilistic CSP power output model into the production simulation framework. The simulation is run in the same way as in the conventional approach, but the computation is conditioned on each of the R regime we constructed previously. Subsequently, we can compute the expected volume of the matrix of interest as the regime probability weighted average we get from each computation. And here I'm going to give some representative results from 3 different case study sets to give us an insight about how the CSP will impact on the power systems. For each study, we run the 1-year simulation, so as we can focus on the setting the characteristics of the approach. The basic study test system is a modified version of the IEEE reliability test system. We scaled down the 2011 ERCOT load with annual peak load with a 3,050 megawatt annual peak load, and here is the total capacity of the conventional generation resource mix. In the first case study, we perform a sensitive analysis of the CSP capacity. we consider a single CSP resources located in the Midland, Texas, with its capacity in multiples of 60 megawatt and 6-hour thermal energy storage. Here I'm going to explain why we use hour and megawatt hour to describe the capabilities. The physical capability of a storage is the maximum amount of thermal energy can be stored in the storage. The storage capability expressed in hour means, for example, the 6-hour thermal energy storage for a 60 megawatt plant means if the storage is full, this plant can produce electricity at its full capacity only using the thermal energy from the storage for at most 6 hours. In the first study,
you should go back and explain what is that which is going to be outputting as a energy. What is the capacity of generation there?
what?
You have that in megawatt hour thermal,
Mm-hmm.
and you're going to be using it for 6 hours. So you should be able to express now as a result.
Okay. For example, the 6-hour thermal energy storage are the same as the same for the thermal energy, the physical capability with 840 megawatt hour. It means a 6-hour thermal energy storage for a 60 megawatt CSP can store like 840 megawatt hour thermal energy in the storage. Do you mean?
The 60 megawatts, that's the CSP capacity.
Yeah, that's the CSP output, the plant capacity.
But what is the output of this thermal energy storage?
That's the maximum amount of the thermal energy can be stored in the storage.
Yeah, but how does it help on an hourly basis?
What, this hourly basis?
Yeah.
Okay.
Behind the screen is a eraser and some markers.
Can we use it? Oh. If the storage is, for example, for the example here, for a 6-hour thermal energy storage, if the storage is full, it will store 440 megawatt hour thermal energy in the storage, and in each hour, the power block can withdraw at most 140 megawatt, 40 megawatt thermal energy to generate 60 megawatt hour energy in 1 hour. It means if the storage is full, the storage can supply the plant to generate for 60 megawatt hour energy in each hour for at most 6 hours. Do you mean this? Okay. Finally make it clear. In this study, I choose the production cost, the CO2 emission, loss of load probability, and expect unserved energy as the metrics of interest. We can see the implementation of the CSP resources lower the annual production cost and the CO2 emissions. Here. Similarly, we can also observe the reliability improvement due to the CSP integration. But we can observe that every the reliability improvement of every successive increment has smaller impacts than the preceding increment. We call it the diminishing returns. It's a long linear behavior. In the second study, we aim to investigate the impacts of the thermal energy storage capability on the CSP constructions. We consider a single CSP resources located in Texas with 120 megawatt capacity and variable thermal energy storage capabilities. We list the 7 cases here with the storage capabilities ranging from 0 to 6. We can see as the storage capability increase, the expected annual CSP energy production increases, but it reached a saturation around 4 hours. It is because the amount of thermal energy can be received by the CSP is fixed. We cannot increase more. So even though we can increase the storage capabilities, we do not have enough solar energy to store, so we cannot make full use of storage. So we can use this approach to do some investment analysis, because it will be a waste of time to invest on like 60-hour storage here. Sometimes one of the characteristics of the renewable energy is its variability. So when we design some when the system want have some multi-sites renewable resources, they want the hourly output become as smooth as possible. In this study, we consider 4 possible CSP sites with 60 megawatt capacities. We want choose 3 out of 4 on the basis of the smallest aggregated output. It means we want the standard deviation of the hourly CSP output becomes as small as possible.
Narrow band. Within a narrow band.
Yeah. Okay. Yeah. So sometimes because the solar energy may be not, it may be less during one day, but may be sufficient in another day. So we may set up a band and try to make the hourly output curve is with various in its band and don't violate the limit line we set in previous. We have 4 alternatives here, and each alternative is run with or without 3-hour thermal energy storage with each CSP. Here we can see the alternative 4 has a smallest standard deviation of the hourly CSP output, but it's still very high. Like it's the total capacity is 180 megawatt, but the standard deviation is around 50. So it's still very high. With the storage, we can see the storage is able to smoothen the standard deviation, but it's still very high. It's around 40. So maybe we can like I read some reports from a plant. It's a very small plant. It's just 10 megawatt, but it has a 10-hour 15 hours thermal energy storage. So its output is almost is almost aligned, but with a bound like from 9 megawatt to 11 megawatts. So it works like a very conventional coal plant. Finally, I'm giving some concluding remarks about my research. This approach is able to quantify the impacts of the integrated CSP resources on the production cost, CO2 emission, and the reliability. We can also say that implementation of the storage provides some controllability and the dispatchability of the CSP resources. The storage can increase the total energy production volume, because we can store the energy to produce it during the time when the energy is more expensive. We can also say the siting of the CSP resources can kind of smoothen the output of multiple sites. In the future, actually that's what I'm doing now. I consider different objectives in the scheduler. I investigate the substitution capability of the CSP resources for replacing the retired conventional generation capacity. Like if there is a 100 megawatt CSP resource, a 100 megawatt gas station retire, what the size should be for CSP resource, like maybe 200, 400, or 500. I also want to have some study about the interactions between the solar resource and the wind resource, because the solar resource has its peak power output during the day, but the wind may have the peak power output during the night. And finally, hope someday I can incorporate my this model into into a system with considering of the transmission loss. Okay, that's all. Any questions? Any question?
I have a question. I wonder why they do this CSP instead of just use a regular solar power plant with PV cells and store the energy in some other way, like in giant capacitor banks or with pumps.
Yeah. And Josiah just asked are you asking about storage stuff?
Yeah, I'm asking why CSP instead of storing, why store it as heat instead of as some other thing?
Because okay. Josiah just asked that why does CSP store the thermal energy in the plant, right? Yeah. Actually, CSP is an indirect way to convert the solar energy into electrical energy, because it will convert the solar energy into thermal energy first, and convert the thermal energy into electrical energy. And I think it's cheaper to store the thermal energy in the storage. It's actually it's inner storage. It's an inside storage for plant. We can also set up some storage device to store the electricity, but it's much more expensive for increasing the capabilities for the storage. So, any more? Okay, I think that's.
Send everybody who asks questions, you send them all to maps, right?
Okay.
Good strategy.
Maybe I will do like next time. Okay. So no questions? Okay, thank you.
Well, our next presenter is Kai Van Horn. Kai received his BS in multidisciplinary engineering from Purdue in 2007 and his master's in electrical engineering here at U of I in 2012. He's currently a PhD candidate working with Professor Gross.
Are we good? Am I on? Oh, I can do this one again. No, I'm just kidding. I'm just kidding. Oh, sorry. I'm sorry. I'm sorry, Kevin. Sorry. All right, so this summer I did an internship at the Brattle Group. They're a consultant that does a lot of work in the energy industry, and some of my work was related to renewable integration. So one of my colleagues presented this at the general meeting in July, and so I'm just going to kind of give an overview of these ideas and give this presentation. So basically what I'm going to talk about is the challenges posed by integrating renewables into the system, and then talk about how the transmission planning procedures that are in place may not be able to represent the opportunities for transmission to address some of those challenges, and then maybe how we can adjust the transmission planning that we do so that it can address those challenges, so that it can show how transmission can be used to address those challenges. So I'll start with talking about traditional transmission planning, just to give an overview of that, and then I'll talk about renewables and the challenges they pose, and we'll talk about transmission planning under deep penetrations of renewables, and then talk about how we can bring that all together and represent renewables in the transmission planning.
Traditional is very similar to conventional.
Yeah, we can call it conventional too. I know you prefer that word.
I don't think there's much tradition as far as I know.
Okay. All right. Thank you, Professor. There. So the microphone just came on. So what I'm talking about here is the high voltage transmission system. So what this is it's the backbone of the grid, really. It's where many of the generators are interconnected, except for maybe like rooftops, solar, and things like that. That's where the distribution companies would receive delivery of electricity to deliver to our homes and to our small businesses across the substation. And then there are a few large industrial customers that are connected at this level. The system is mostly characterized by non-routable flows of electricity. As we know, Kirchhoff's laws can't be violated, and absent large amounts of high voltage DC or fax devices or something of that nature, you can't control where the electricity flows. And this is important in transmission planning because if you build a line in one place, it's going to impact the flows everywhere else. Transmission planning is also characterized by long development times. There's a lot of processes that must be gone through. If you want to build a transmission line through many states, you must receive approval in each state. You have to get right-of-way. And luckily, and also high upfront costs. And luckily, the lifespan of these resources is long, and so this often justifies the long times and the high upfront costs. But the main role of this system, as I mentioned, is delivering energy from generation to load. It's the transfer capability in our system allows the basic role of the electricity system to maintain the supply-demand balance so that when we flip our switch, the lights can come on to happen. A secondary benefits of having a transmission system or having a transmission system with additional transfer capability are increasing the reliability. So if there's a contingency, the system doesn't go down. And then also there's economic benefits through the sharing of reserves from different balancing areas. Since the United States is not one giant grid, it's 3 grids. And then within those grids, we don't have a single authority responsible for maintaining the supply-demand balance. There are hundreds of smaller authorities which maintain the balance. And so if you have interconnection between those different areas, then you can share reserves across those areas. So longer-term planning typically, though, has been done to maintain the reliability of the system. This is the primary goal of transmission planning, is to, at the least cost, make sure the system can be reliably operated. Given assumptions about how the load's going to grow, where generation is going to be built. And so typically they'll look at the peak load plus the reserves, and over a planning horizon, and because of the long time scales, here's maybe 10 or 20 years, and look at on an annual basis perhaps the peak load and plan the system for a certain set of projects that have been proposed or a set of projects that have the potential to be built. You would evaluate the system with or without those projects with these load assumptions, and then also with some assumptions about the reliability in the system, whether or not there's, for a credible set of contingencies, generator or line contingencies, whether or not the system is stable for a few snapshots. And so what I mean by snapshot is that you take the system at a point in time with a particular load, and with all the generators and lines in place, the structure of the system is not changed, and you see if it's possible to meet the load under that scenario. And so those would be reliability-related scenarios. And this is typically, or this is conventionally how we've performed transmission planning. You do a few scenarios for maybe different load scenarios, high load, low load, maybe seasonal, and you arrive at the least cost portfolio of transmission projects that will allow the reliability criteria to be met. And these are, as Terry mentioned in his presentation, are loss of load probability in any hour or expected unserved energy. And what we found also, or what's been shown also, is that the unique characteristics of renewables, which I'm going to get to next, they don't really lend themselves well to this because mostly this is static. There are some dynamic studies that are done when you do transmission planning for dynamic stability reasons, but those are very short time scale, and they don't address the issues with renewables that I'm going to talk about. But what's been shown is from renewable integration studies is that transmission is a very important part of integrating renewable energy. And so if that's true, then we need to integrate those important aspects of the resources into the transmission planning process. So as you may know, the wind and the sun, they don't operate by our will. They are natural forces and are variable and intermittent. So I'm showing here on the left the average wind output in megawatts for each hour of a particular year in each season. So this is averaged for each hour in the season. And then in the bottom, this is the same lines in the middle here, the mean, and then the max and the min value here. So you can see, I mean, there's huge variability in the output of the wind farm. And so putting this back in the transmission context, if you're looking at single snapshot of the system to see if the system will be stable, or if the supply-demand balance or the reliability criteria will be met, if you go from 1 hour to the next, the renewable output may change considerably. But if we're looking at single snapshots of the system, we can't capture that. So and there are other aspects of this too, is that this tremendous variability requires additional flexibility in the system. It requires more units that can be ramped up and down and quickly, and then also and which also can be which we can also achieve by installing transmission, so that you can use units from one area to meet reliability, or I'm sorry, flexibility, or to have additional flexibility in other areas.
You haven't defined flexibility, have you?
I can talk the flexibility. I guess I was just saying flexibility is like the ability of the system to respond to changes. So, for instance, if there's a large ramp in the renewable, there isn't really a single metric that's been defined for flexibility, but we often talk about flexibility in terms of the ability of the system to respond to ramping. That's one proxy for flexibility. So if a system, and ramping is defined as the rate of change that a generator can go through over the time it takes to go through that. So for instance, like 10 megawatts per minute. If it can raise its output 10 megawatts in 1 minute, then that would be its ramp rate. And so when we don't have a lot of wind, the load shapes and the load we face is relatively predictable, and we know that has some diurnal pattern, and so we can schedule resources, and we can be fairly well assured that we'll have enough ramping capability to meet that load. But when you have like stochastic resources like wind, and now you're trying to meet the net load and not the total load, then the ramps in the load may turn out to be much greater than you thought, and if you don't have enough rampability in your generation fleet, you may have loss of load events or something similar. And this is one way that transmission, by interconnecting systems and allowing additional generation to be used simultaneously to increase the ramping capability of the system. That's how transmission could provide flexibility, or could at least harness flexibility. It's not providing it really. So one thing to look to kind of understand the importance of flexibility and the importance of this flexibility requirements in integrating renewables is to look to island studies, because these are small systems that have been built out with renewables that represent a significant proportion of the total generation. And so we can kind of see what happens if we have a ton of renewables, and what are the impacts of things like flexibility on renewables, and then also the impacts of different types of operating reserves, and how we determine the amount of operating reserves and the type of operating reserves that we keep. And so from those studies, we see that these are critically important aspects of integrating renewables. You really can't do it without them unless you're going to curtail most of the renewables that you're generating. And so these considerations then, if they're critical aspects of integrating renewables, need to make their way into transmission planning. And so now we kind of have this coming together of the traditional transmission planning where we consider like worst case scenario to meet the reliability requirements, but then we also consider like the dynamics of the renewables and how bringing transmission in with renewables can bring about geographical diversity to reduce that variability in the wind, and also bring more flexibility by allowing us to exploit generation in more different locations of the system simultaneously. So under a single framework, this will...
The generation is fixed, isn't it?
What do you mean fixed?
Location of the generation.
Yeah, but so the generation can deliver electricity. It's not constrained by transmission to deliver electricity.
But you said you're putting generation at different places.
Oh, okay. Yeah, I'm sorry. I meant that the generation has the capability. There's enough transfer capability for the generators to deliver energy to meet the load. Yeah, or to deliver rampability in order to meet ramps in the load, more specifically. So bringing these together, if we want to plan the system or have a transmission planning processes that can account for that can basically capture the benefit of transmission for integrating renewables, then we need to assess the impacts of transmission on things like operational flexibility. And we need to expand from just as evaluating reliability metrics to evaluating other metrics or cost metrics, and we need to think about the time scales and the over which the studies are being done. So just to give an idea of why time scale is important. So if we think about a single day, this is wind output for a single 24-hour period, and in each chart the wind output is averaged over successively longer intervals. So in here, there's another line in here, but don't worry too much about that. But the maximum and the minimum of the second line, the averaged values are shown. And so as you can see, the important thing here is that as you average over a longer period of time, basically you're bringing those lines closer together, closer to the mean output of the wind. So you're failing to capture some of that variability. And so basically, if you're not capturing this variability when you're doing a study, if you were using, I mean, this is 1 minute data up to hourly, so even over this scale, if you're using hourly, which is very common for doing these types of studies, you're already going to be missing like about 40% of the variability in this wind output, which means that you're not capturing all of the value that transmission could bring in addressing the impacts this variability has on the operation of the system. So this just shows again that as you push if you average over longer periods of time the data that you're using for wind output, you're really losing that variability. So going up here now to up to a day, you can see that the variability of the wind output here is lost. And so really we're not capturing that flexibility that we aim to capture if we want to characterize the value of transmission for renewables.
I capture flexibility because you don't capture any kind of variation.
Mm-hmm.
If you take one picture in 24 hours.
Yeah, I'm not saying that. I'm saying that that's what we don't want to do. That's what we do now, is take snapshots, maybe every 24-hour period, or maybe every season we have a single scenario or a single power flow that we're using for planning purposes. I'm saying that what we need to do is we need to use a finer granularity, and we need to do studies that can capture, by using a finer granularity, these faster dynamics. But then there's also slower dynamics that need to be captured. I mean, clearly the wind output this year from all the collective wind farms won't be the same as the wind output next year from all of the collective wind farms. And if our planning takes place considering the fifth percentile of wind output, then we're not going to capture all of the benefits that the transmission can bring the benefits of transmission in order to integrate renewables. And so this is another consideration that needs to be integrated, to do multiple scenarios with wind, or capture through other methods, such as, I mean, Terry's probabilistic simulation framework is one way to do this type of study. So, I mean, basically, what we're talking, what I wanted to get to at the end of this was that the way that it, and Professor Gross alluded to it just now when he was mentioning the 24-hour period, is that we really need to address the issue of integrating these faster dynamics into transmission planning if we're going to fully value transmission infrastructure for integrating renewables. We need to do it in order to assess the value along, many metrics. The expected value of the wind output is just one, and the intra-hour variability is not being captured if we don't look intra-hour. So, and these large ramps can be very important. I mean, we've had blackouts that were arguably caused by large ramps in the wind, and so if we fail to capture such things in the transmission planning, then those events have huge amount of value, and that's value that's lost that the transmission could bring. And then also just the slow dynamics, thinking about the wind output over the course of a year and other slow dynamics that can be integrated into the wind planning process. So,
I'm really concerned about this term dynamics because in power system, we use that with respect to dynamical regimes. And you don't mean anything here which is of the dynamic nature.
Okay.
Right? I mean, you're not looking at transient stability. You're not looking at dynamic response of a power system.
No.
Just are looking at dynamic flexibility.
Yeah, but we don't call it dynamics because that conflicts with power system dynamics.
So what term do we use?
Well, you can say the time variation of wind.
Okay.
So that's the danger of applying what we know.
Yeah.
Yeah. So just to conclude, planning under deepening penetrations of renewables requires considering a finer granularity and considering the unique characteristics of those resources so that when we do these planning studies, we capture the value that those projects can bring to integrate renewables. And that means looking at to capture the time or the uncertainty that renewables bring through finer granularity studies and to develop metrics that can assess the value of flexibility and how transmission can bring additional flexibility to the system. And I think one of the other takeaways here is that planning in this new world that we're in now in the power system with lots of uncertainty with generation output, it requires looking at more than just reliability, especially when we have in this country, we have RPS and other environmental regulations that are driving decisions on the power system. We can't consider reliability alone. And renewables have really just made that clear because they're here in large quantity and they promise to be so in the future. So these are my mentor and my manager at the Brattle Group, and thanks a lot.
So that was a Canadian outfit?
No, they're in Cambridge, Massachusetts. That's their home office, but they also have offices in DC and New York and San Francisco.
Because something said, oh, the conference was in Vancouver.
Yeah, the conference was in Vancouver, sorry.
Okay, so I
Yeah.
thought they were Vancouver.
Oh, no.
Wow, what a great place to do.
Yeah, that would have been great.
Two things. You see any assumptions about storage? They're just assuming storage is not going to be able to scale to be useful.
Oh, no, I mean, this is, I think, even higher level than that. You could definitely include assumptions about, or you could include the considerations for storage in the studies that you do. I mean, that would be part of the scenarios that you develop in order to do a planning study.
Okay, and so then I guess the question is, are you just trying to tell us, is this intended to be backward information?
Yeah,
What's
I mean,
the conclusion to be drawn?
I mean, the conclusion to be drawn here is that conventional planning fails to capture those impacts of renewables that would be valuable for that transmission could be valuable to address. So, for instance, if you have two systems that are loosely connected, maybe there's often congestion between them, and you add a line, and in both systems you have wind. If you add that line, then the net variability between those wind projects is going to decrease. So it makes operating the system easier. And so that some portion of the benefits of adding that line could be attributed to that reduction in variability that translates into a reduction in the need to hold operating reserves and things like of that nature, and a reduction in the need for additional flexibility or ramping capability in the system. So, I mean, there are many components to the benefit of a transmission line, and so this is kind of getting at one, which is the benefit of transmission for integrating renewables.
Okay, so I don't want to beat that horse,
Mm-hmm.
but it seems like we've talked about this, and this is not new.
Yeah.
So is that,
I mean, I don't know. I think that maybe it's not new, but it's definitely not part of the typical, or it's not part of the like day-to-day planning processes yet.
oh, I see, so that's the
Yeah.
challenge.
Yeah. I mean, I think that, you know, I guess I would say
Is there any metrics associated with what you're describing over here?
metrics related
I
to.
mean, you put dollar signs to it. Those are metrics. And you put dollar signs. When you measure this flexibility, I mean, I see qualitative description,
Mm-hmm.
but are there some metrics which you're deriving that you're using that can say that this transmission plan is better than as the other transmission plan for the following reasons in terms of the metrics that you use?
Well, I mean, I don't think this presentation puts forth a specific approach. I think it's part of.
I'm talking in general.
Yeah, I understand. I think the purpose of this presentation was to facilitate a discussion about how we do transmission planning and how we can do it better in the face of integrating renewables. So, I mean, yeah, there are metrics we can use. I mean, we can definitely assess the average or the adjusted production costs in the system when you have these different scenarios to get at the value of flexibility. If you put a new line in the system, you can see how much the production costs were reduced by adding that line, and that can be that's one component of the benefits.
Perhaps increased.
Or increased even, yeah. I mean, that's also true.
So are there industry standards for conducting a planning? You have what, 23 or 3,200 utilities out there.
Mhm.
Each one of them could do it.
I'm not aware of like a codified standard that says you have to do it this way. I mean, there are considerations that are required, like, for instance, the FERC put forth Order 1000 saying that you have to consider public policy requirements in your transmission planning, which means you have to consider the impacts of RPS and things like that.
Those are all regional standards, so they are reliability standards.
So for instance, you got a WEC. WEC is going to define those for.
So WEC will have one, and somebody in the east will have another one. Florida Reliability Council, totally different one.
So
It's not like nationwide.
And it's not regulated by the operator.
I mean, it's regulated because FERC's idea is to have more and more standards so that they can hold the feet of the utilities to the fire, because they didn't they did things that they did not comply with the standard. So, you know, Florida Power and Light got $25 million fine from NERC because they didn't do things according to the standards.
Mhm.
So it's on the radar of every risk officer of a company in terms of what they do to meet the NERC requirements. So there are standards, but not in terms of flexibility, because we don't have yet well-defined metrics for that.
yeah, and correct me if I'm wrong too, it's that the standards that are in place are more like benchmarks where they don't dictate how you do the process. They say what the result of the process has to be. Like you have to show that the reliability in the system will at least meet this standard, like this benchmark.
So you essentially have left and right limits.
Yeah.
You got to be between.
Yeah.
So
Yeah.
that's the standard.
Yeah.
The issue is that what we need is you need to build more transmission to integrate those resources.
Mm.
Because currently, if you go to a transmission provider, said we can give you service. We can give you service for 8,755 hours, but for 5 hours of the year, we cannot give you service. It could be the 5 peak hours.
Mm-hmm.
Guy can take it, or says, no, I need a contractual service for every hour that I generate electricity. Well, he can't give it to you. Says, well, FERC says then you have to build. In order to build, you have to go to the states to get your permits, and so that long and arduous process can get to 16 years, and you still haven't put any kind of hardware into the ground. So by that time, the penetration of wind resources has changed measurably. So whatever plans you had, it's useless.
Mm.
Well, you're not supposed to think such a gloomy picture.
Well, but that's why we're not building enough transmission.
Mm.
Transmission is really the Achilles heel in the North America.
We have multiple states now, which make multiple companies.
Yeah, and so the big difference is if I want to build a gas pipeline, I go to FERC, I can do one-stop shopping, and I get a permit for all the states through which my pipeline goes. If I want to build a transmission line from Texas border or Oklahoma border to Chicago City Gate, I have to go through 8 intervening states, and they are supposed to approve that line, which may not necessarily benefit their own residents.
Then they have to figure out how to tax it, don't they?
Well, it's not that taxing the flow because that goes according to Kirchhoff law, and that they can't override here.
I know, but they could put a meter on
Well, I'm sure they could.
Yeah, but that's codified in the open access transmission tariff that on file at the FERC. So, so Matt has a question.
Yeah. So I think it has to do with like slide 2 or 3 or something.
Oh,
Where
okay.
you say that it's good because transmission lines cost a lot, but they last a long time and they take a long time to plan. So I read an article in the PS magazine about how like a lot of big companies, like big energy users, are now building on-site, energy like power generation, like Walmart, Google. So let's say that like something like President Gross said, it takes 16 years for a transmission line to go on. Is anyone expecting that a lot of these companies are now going to produce their own electricity? So maybe the requirements are not as large. Is projection changing now? Is that being factored in at all?
Yeah. So Matt's question is whether or not the implementation of like on-site generation and distributed generation is going to affect the transmission that may be built in the future, whether or not it's even needed. Is that right?
Yeah,
Okay. So yeah, I mean that's a huge deal actually. There's a lot of speculation right now about what the impact of distributed generation and on-site generation. I think I read something just recently about Walmart thinking that it was going to meet like 40% or 20% of its like energy needs through on-site solar in the next decade or something. It's an enormous amount of energy for such a large company, and that definitely would have an impact. I mean, in the up to now, we've had mostly flow of electrons across the substation into the distribution system, and if you have a lot of customers in the distribution system that now are producing energy, that could even change. It could start flowing back onto the transmission system, and those are a whole bunch of issues to address with that. But definitely, that has a huge impact on whether or not we even need to build transmission lines.
So this like average approach where you don't have the small variability or the very fine dynamics, you actually prove like it'll work in the future if you take away more loads, right?
Like if you're thinking, like you mean taking like snapshots year upon year, if you were forecasting that your net load was actually going to like start declining, then you could capture that dynamic, in some way.
Well, you could, but I think the issue is that's a very tough question that you're asking. And I'm of the opinion, and so I'm very prejudiced that way, that we've had airplanes come in, and we have automobiles, and we have tractors and so forth. We still have trains. And the train is still the most important mode of transportation for getting goods to the market in the U.S., notwithstanding all those other means of transportation. So I'm of the opinion that we built the transmission system because we need to have that backbone in the U.S. And I think the problems are going to come when those guys are going to be forced out of the system because they're still relying on the local utility in case the sun doesn't shine or the microturbine doesn't work. They're connected to the utility, so they'll just get the juice. So either the utility is going to put in like, we'll give it to you, but we'll zap you such a high charge that you'll be seeing stars when you get your backup energy from us, or you could keep contributing to our infrastructure. So what you're describing now is called in the utility industry the death spiral. So you have all these guys who are going to go and generate on their own rooftops. In California, they get feed-in tariffs. So people are building larger solar plants than they need. They produce electricity. They end up not paying anything to the local utility because their net feed-in is higher than their consumption. So a lot of people are doing this. So all of a sudden, these guys are not contributing to the infrastructure in terms of distribution, the reliability, and so forth. So what does this do? It forces other people. These guys have a good idea. Let's do the same thing. So it reinforces that. So finally, it's going to be just the very poor people who have to pay all those high rates, and they won't be able to afford it. So this is a very, very bad situation, and I think there's going to be some policy.
Yeah, of course, if the utility decides they want to be the supplier of those local energy resources.
Of course. I mean, that's going to be a different utility.
Instead of,
solar or us.
Yeah.
Yeah, I mean, that's going to be a different utility. But this is very serious now in states like California and Arizona. There's a lot of cooling and awing because it's striking very close to home. I remember when I was at PG&E in 1990s, early 1990s, late 1980s, we thought those little microturbines are going to be eating our lunch because every McDonald's was supposed to put one of those little microturbines on the roofs to run the local McDonald's. Hasn't happened yet. So I don't think those companies really want to be in this business. I really don't think so. And I think there's going to be some accommodation, but we don't know yet because in the U.S. all you need is to have one comma put in the right piece of legislation and then you're protected.
Yeah, it's really interesting that saying because what I asked you, San Diego, and they were talking about the impact of solar arrays just on homes in terms of they're getting revenue to build the infrastructure. And so it goes beyond businesses to actually residential.
You can do it better. The people who will give you half of the benefits if you give them your rooftop to build their unit and they own it. You don't own it.
All right.
Bill is smiling because he will sell those inverters. It doesn't matter who is buying them.
All right.
So it's cheaper than utility power right now. So.
I mean, it's really this is the kind of competition they don't know how to deal with because they haven't contemplated it. Okay, but that reliability where you bury stuff underground and you have to feed that and you have to maintain it, you have to have millions of customers pay for it. If they're going out the system, then it raises the rates of everybody else.
Well, the problem is the legislation is we have written not permit to charge fee for infrastructure.
Well, they don't, but it screws the rates that they amortize those investments. I mean,
It's an
because there
incremental
won't be
charge.
people to charge it from because people are leaving the system.
So you say there might be policy put in place. What kind of policy? The government can't come in and tell people that
No,
they
not the
can't.
government. The comment is very willing to write the legislation because they would like the assemblyman in Springfield to pass. Okay?
Well, nonetheless, but I mean, you can't regulate whether or not someone puts a solar panel at their location.
Well,
right?
no. But you can regulate that. You can put as large a panel as you want, but we cannot have you sell more electricity than your load. Okay, so if you want to donate that to the system, fine. We love your donations. No tax deductions are given, but we'll take it from you. We'll help you with it. But I mean, when people exceed their own load requirement, then it becomes a little bit problematic. Just everybody generating 10% more. If you have enough of those bodies, it starts hitting those utilities. I think the interesting here in your presentation is to get some quantitative metrics so you can evaluate those benefits.
Yeah.
Otherwise, we can do hand waving together.
Yeah. On Friday.
We can do it Saturday too, but it's cost extra. You have to